Welcome to Thought Frontier.
All right, get ready, because today we are going deep on something seriously mind-bending.
Yeah,
The holographic principle.
that's right.
This is the idea that our universe might actually be a 3D projection from a 2D surface.
Exactly.
Like a hologram.
Yeah?
You sent in a ton of articles and research on this.
You did?
So clearly you are fascinated by this idea.
Definitely.
As am I.
It's a fascinating one.
I gotta say, when I first heard this whole, universe as a hologram thing, I kind of pictured, those cheesy rainbow stickers you get at, amusement parks?
Oh, yeah?
But after digging into this with our expert,
Right.
let me tell you, this goes way deeper than that.
It really does.
It is not just some, far-out theory.
No.
This idea comes from trying to solve real puzzles in physics,
That's right.
especially when we start looking at black holes.
Exactly.
Okay, so black holes,
Yeah.
everyone's favorite cosmic vacuum cleaner.
Right.
How do they even connect to this hologram idea?
Well, it all starts with this thing called entropy.
Entropy.
Yeah, you can think of it as a measure of disorder, or even how much information something can hold.
Okay,
So like a messy room would have high entropy.
gotcha.
A perfectly organized library would have low entropy.
Okay, so entropy equals chaos level.
Exactly.
So where do black holes fit into all of this?
Well, the strange thing is that a black hole's entropy isn't related to its volume like you would expect,
Okay.
but instead to its surface area.
Huh.
Yeah, it's kind of like saying that the number of books you can fit in a library depends on the size of the walls
Right.
and not the space inside.
Wait, that's totally counterintuitive.
It is.
You would think it would be about the volume,
Exactly.
not the surface.
Exactly. And that's the clue that led to the holographic principle. It suggests that all the information about everything that falls into a black hole
Yeah.
isn't stored inside,
Okay.
but encoded on its surface.
Oh.
Kind of like a hologram.
So instead of all the books being inside the library, all the information about all the books is written on the walls themselves.
Exactly.
That's wild.
It is.
That's a crazy idea.
It is a crazy idea.
Okay, so now things get even weirder when we bring in Stephen Hawking
Oh, yeah.
and his discovery that black holes actually radiate energy.
Right. Hawking radiation.
Hawking radiation, exactly.
Yeah.
Didn't he also say that black holes eventually evaporate because of this?
They do.
Yeah.
That's exactly right.
Okay.
So here's the problem. If black holes are radiating information,
Right?
and information can't be destroyed according to quantum mechanics,
Exactly.
where does all that information go when the black hole is gone?
Right. That's the information paradox. You've got general relativity saying that information should get trapped inside the black hole.
Right.
But then you have quantum mechanics saying that information can never be truly destroyed.
So we've got this clash between general relativity and quantum mechanics.
We do.
And the holographic principle is trying to make peace between them.
You got it.
Yeah, the holographic principle suggests that information isn't lost, but instead it's encoded on the surface of the black hole, even as it evaporates.
Okay.
And this brings up the really mind-blowing possibility.
Okay.
Could our 3D reality actually be a projection of information
Whoa.
that's stored on some distant 2D surface?
Okay, from messy rooms to the fate of the universe,
That's right.
our listener must be thinking, I signed up for a deep dive on holograms, not an existential crisis.
Right,
But in order to understand this whole holographic universe idea better,
right.
we need to venture into some pretty complex territory. String theory and M theory.
That's right.
And full disclosure, even I get a little lost in the world of tiny vibrating strings and extra dimensions.
Yeah, there's definitely a lot to wrap your head around.
It really is.
But essentially, string theory says that the universe isn't built from particles,
Right.
but from these tiny little vibrating strings.
Yeah.
And then you've got M theory, which tries to unite all the different types of string theory
Okay.
into one big framework.
So strings instead of particles.
Strings instead of particles.
But what do these theories have to do with the holographic principle?
The amazing thing is that string theory and M theory naturally incorporate the holographic principle.
Huh.
They actually provide a mathematical way to understand how information could be encoded on a boundary,
Yeah.
which is exactly what the holographic principle suggests.
So we're seeing this idea pop up in black holes.
Right.
Now, string theory
Yeah,
starting to feel less like a coincidence, wouldn't you say?
absolutely.
Yeah, okay.
But the story doesn't end there.
Okay.
This is where a physicist named Juan Maldacena enters the picture.
Juan Maldacena, okay.
Yeah.
Now, that's a name that is synonymous with some serious physics wizardry.
He's done some groundbreaking work,
He really has.
especially with something called the add-SCFT conjecture.
Okay, hold on.
Yeah.
Another dimension.
We're adding another dimension.
Are we diving into the matrix now?
Not quite, but it is just as mind-bending. So, in simple terms, the add-CFT correspondence is a mathematical link between a 5-dimensional universe
Okay.
and a 4-dimensional boundary.
So everything happening in that 5D universe has a corresponding description on that 4D boundary.
Precisely.
Wow.
And this has been shown to hold true in specific examples involving black holes. So, in this framework, black holes in the 5D space are mathematically equivalent to a specific type of quantum field theory on the boundary.
Okay.
Again, it all points back to that idea of information being stored on a surface.
Okay, I'm starting to see the bigger picture here.
Yeah.
The holographic principle pops up in black holes.
It does.
String theory. And now we've got Maldacena giving us a mathematical way to describe it.
Exactly.
And this is the big question.
Right.
Does any of this apply to our universe?
That's the question.
Because ours doesn't seem to have a clear boundary like in this add-CFT thing, right?
That's the million-dollar question.
Yeah.
Is this just a cool mathematical idea, or could it actually describe the universe we live in?
Right.
And that's what physicists are really trying to figure out right now.
Yeah.
And it's a tough puzzle to solve.
Well, I know our listener who is clearly passionate about this topic is eager to hear more.
Absolutely.
So let's move on to how scientists are trying to apply these holographic ideas to cosmology
Okay.
and see if we can find any evidence for them in the real world.
Let's do it.
All right, let's dive in.
Let's go.
Okay, so we've gone from black holes to string theory to a 5D universe with a 4D boundary.
Yeah.
It's a lot to take in.
It is.
But the big question is, how do we connect all of these like really elegant theories
Right.
with the messy reality of our own universe?
Right, because our universe doesn't exactly come with a neatly defined boundary,
Right.
like in the add-SCFT conjecture.
Right, exactly.
But there are some fascinating attempts to try and bridge that gap.
Oh, okay.
One approach uses what's called the domain wall cosmology correspondence.
Domain wall cosmology correspondence?
Yeah.
That sounds intense.
It is, but the basic idea is actually pretty cool. It's a way to map the evolution of our universe onto a theoretical domain wall spacetime.
Okay.
These domain walls are kind of like simplified models of the universe that we can study using holographic tools.
So it's like we're building a holographic model of our universe.
Exactly.
Even though it doesn't have that clear boundary that we talked about before.
Exactly. And this allows physicists to study scenarios where gravity is incredibly strong,
Okay.
like in the very, very early universe.
Right, like right after the Big Bang.
Exactly.
Which is really important because like our current models of the early universe, like inflation,
Right.
they kind of break down when you try to apply them to like those extreme conditions, right?
Exactly. So holography could actually give us a whole new way to look at the Big Bang
Wow.
and the origins of the universe.
So it's not just like a cool theory,
Right.
it could actually like unlock some of the biggest mysteries of the universe.
It very well could.
That's what I'm talking about.
Speaking of unlocking mysteries, remember that cellular universe analogy from the sources you sent?
The one where the universe is like a giant cell?
That's the one.
Okay, yeah, that was wild.
It's pretty mind-blowing, but the idea is that there are some surprising similarities between the structure of the universe and the biological cell.
Yeah,
For example, the supermassive black hole at the center of our galaxy
okay.
can be compared to the nucleus of a cell.
Okay, I can see that.
Yeah, they're both these dense central structures that seem to control a lot of what happens.
Right.
And just like the cell membrane regulates what goes in and out of a cell,
Yeah.
the event horizon of a black hole acts as a boundary, controlling what can enter and what can escape.
And then there's the fact that like both are expanding.
Right.
Like the universe is expanding outwards.
Right.
And cells like grow and divide.
Exactly. You're catching on.
Okay.
Now, it's important to remember that this is just an analogy,
Right.
but it's a pretty powerful one.
Yeah.
Because it shows us that these holographic patterns could exist on vastly different scales of reality. From the entire universe down to something as small as a cell.
It's like this whole universe as a hologram thing keeps popping up everywhere we look.
It really does.
But, you know, analogies are one thing.
Right.
Hard evidence is another.
Exactly.
Is there any way to actually test the holographic principle?
Yeah, that's a great question.
Like, how do you go about proving something like that?
It's definitely a challenge.
Yeah.
But currently, scientists are searching for subtle clues in the cosmic microwave background radiation.
Okay.
which is like the leftover heat from the Big Bang.
Right.
They're also looking at the distribution of galaxies across the universe.
Okay.
So the idea is that if the universe did have a holographic origin,
Yeah.
it might have left behind some telltale signs.
Okay, so it's like cosmic archaeology.
Exactly.
Trying to find these like faint whispers from the universe's holographic past.
You got it.
Okay, cool.
But there's another really interesting avenue for testing these holographic ideas.
Okay.
And that's condensed matter physics.
Wait, condensed matter physics?
Yeah.
Isn't that about like the stuff that we see and touch every day?
It is.
Like solids and liquids.
Exactly.
What does that have to do with the universe being a hologram?
Well, it might seem like a strange connection.
Yeah.
But remember that AD-S-CFT correspondence?
Right, the mathematical dictionary.
Exactly, that mathematical dictionary between the 5- and 4-dimensional universes.
Yeah.
Well, it turns out that same math can also be used to study certain phenomena in materials here on Earth.
Huh.
Like superconductivity and strange metals.
So the same tools that describe a holographic universe can also explain how like materials behave.
That's the incredible thing.
Wow.
And if we can use holography to make accurate predictions about these materials and then confirm those predictions in a lab, that would be some pretty strong evidence to support the idea that holography is a fundamental aspect of nature.
It's amazing to think that this theory, which started with black holes, could end up explaining things from the beginning of the universe all the way down to the materials we use in our everyday lives.
I know, it's pretty incredible.
But before we get too ahead of ourselves, we need to address the elephant in the room.
Yeah.
Can we actually prove any of this, or is it just a bunch of speculation?
That's the million-dollar question, isn't it?
It really is.
We can talk about these elegant theories and mind-blowing analogies.
Right.
But at the end of the day, science needs proof.
So are we like on the verge of actually proving that the universe is a hologram?
Well, it's the ultimate test for the holographic principle, right?
Yeah.
Can we find that, like, smoking gun observation?
Right.
That takes it from just this fascinating idea to a core principle of physics.
Right.
It's a challenge.
Yeah.
But, like we were just saying, there are some exciting avenues for testing it.
Yeah.
Like looking for those subtle signatures in the cosmic microwave background radiation.
Right.
And the connections to condensed matter physics.
Yeah, it's like we're at the edge of a scientific revolution waiting for that like one breakthrough.
It really is.
That could change everything we know about the universe.
Definitely.
But even if we never find like definitive proof, isn't the very idea that information might be this fundamental building block of reality?
Right.
Like just like matter and energy?
Yeah.
That's a pretty profound shift in thinking, right?
It is.
It could have a huge impact on how we understand everything from black holes to the Big Bang.
Absolutely.
You know, when we started this deep dive,
Yeah.
I was a little bit skeptical, I gotta admit. I was like, okay, the universe is a hologram?
Right.
That sounds like something out of like a science fiction movie.
Yeah, it does have that kind of sci-fi feel to it.
But you've really shown me how these ideas emerge from real problems in physics.
Right.
And how scientists are actively trying to test them.
Absolutely. It's a very active area of research.
It's pretty amazing.
It's been an incredible journey exploring these concepts with you.
Yeah.
I hope our listener has enjoyed it as well.
I think they have.
And, remember, this quest to understand the holographic universe, it's still in its early stages.
Yeah.
Who knows what mind-blowing discoveries await us in the future?
Exactly. Are there any resources that you'd recommend?
Oh,
For
absolutely.
our listeners who want to learn more?
If you're interested in diving deeper into the holographic principle, I'd recommend checking out the work of Leonard Susskind, Gerard Hooft, and of course Juan Maldacena.
Yeah, they're like the giants in this field.
Definitely pioneers in the field.
And there are also a ton of great resources available online, too.
Oh, yeah.
Articles, videos, even online courses.
Definitely.
It's really inspiring to see how many people are, like, engaged with this topic.
It just goes to show how powerful and thought-provoking the idea is.
It really does.
Yeah.
Well, this has been an incredible journey. We've gone from black holes and entropy to string theory and 5D universes.
We have.
And even touched upon that mind-boggling possibility that the universe might be structured like a giant cell.
It's a lot to take in.
It really is.
But it's also incredibly exciting.
Yeah, this is what science is all about, right?
It is.
Pushing the boundaries of what we know and exploring the biggest mysteries of the universe.
Exactly. Sometimes the most mind-bending ideas are the ones that lead us closer to the truth.
To our listener, thank you for joining us on this incredible deep dive into the holographic universe.
Yes, thank you.
Keep exploring, keep asking questions, and never lose that sense of wonder.
That's right.
Who knows, maybe one day we'll all be living in a world where the holographic nature of reality is as commonplace as knowing that the Earth revolves around the sun.
It would be amazing.
That's a wrap for today's episode of The Deep Dive.
It is.
We'll see you next time for another mind-expanding exploration of the universe and beyond.
Looking forward to it.